lose at most? If I started at 110 degrees Celsius and I put it into a 30 degrees Celsius room, yeah, that's the most we could possibly lose. And so we lost 20 degrees out of a possible 80 in 10 minutes. Reduce it down to about 24. In the next 10 minutes, we're going to lose a quarter of what we possibly can. We've now established that sort of, I guess in some sense, rate of cooling. So now that I'm at 90 degrees Celsius, what's the most I could possibly lose?
60.
This is what I'm actually going to lose divided by what I possibly could lose, and that's got to be equal to a quarter. So the math problem is 1/4 is equals x over 60. That's the math problem. X ends up being 15. So putting it back into physics, it loses 15 more degrees. So I was at 90, I'm going to lose 15. I'm now at 75. If we did another 10 minutes, go through the same exercise. I know that 1/4 is going to be the rate at which I'm losing. I'm going to lose it in 10-minute increments. I'm going to lose a quarter of what I possibly could lose. Well, I'm at 75 now, getting down to 30. I could possibly lose 45. The amount I'll actually lose is 10.25, no, 11.25. And so I'll just subtract that from that. And 73 points, no, 6, then I'd be at 63.75.
I guess when doing it, make sure just to look at the problem to see whether you want the temperature change or the actual temperature.
Yes, and there are often times I will ask for the final temperature and people will get as far as the temperature change and stopped.
Oh, the final temperature.
Yeah, all right, at, some increments. So after 10 minutes, that's the temperature. After 20 minutes, after 30 minutes, and so on.
Until it's 0.
Until in the setup right here, it would never actually hit 30. It would just get closer and closer and closer. Realistically, it's going to be within a statistical fluctuation of 30 degrees, or from a physicist's point of view, close enough to count. From a mathematician's point of view, they'll never get there. Cleaning up a mess I made earlier. But the mice will appreciate it.
Now if you take it away.
Well, won't get it all. And no doubt they will vacuum the carpet. Over at Ardmore, when they were renovating the auditorium, and the mice got displaced. So I set up a mouse trap. Ended up killing 4 mice and got a piece of the tail. Yeah, at first I wasn't quite sure what it was, and then suddenly dawned on me that it was the tail. You know, that cheerful hit. All right, Chase, I'm assuming I've answered your question?
Yeah.
Okay, other questions? KB? The tuning fork with a long vertical tube. So we've got 35 centimeters tall, air column. Are you okay if you use different numbers? Obviously, that is the test question upon which the master set problem is based. Let's just say 0.5 meters. And actually, how was that initially worded? No, I'm gonna trust that I have good memory, despite that. It's, first of all, it's heard when we work on. Ah, okay. So we'll say 0.5 and let's make it 1.5, let's just make it big. And then 0.25. So the problem states that when I have a 256 hertz tuning fork, that is when I get the first harmonic. We'll change that to, we'll just say a 300 hertz tuning fork. Although I'm not sure they actually make those. But it's a board problem, we can pretend. First harmonic. I've got an open end and I have a closed end. So I'm gonna have a node and an antinode. The simplest, the first harmonic, will, not to scale, will look like that. So first off, how many wavelengths is this? It is not a half. Yes, it is 1/4. So, since it's the harmonic is happening within the air there, we have 1/4 of a wavelength is equal to 0.25 meters, and so the wavelength is 1.3 meters. All right, so we had the wavelength. The next thing wanted us to find was the speed of sound. Is that the next thing?
The wavelength of the tuning fork.
Okay, so there's the wavelength. So part A was 1/4 of a wave, part B was the wavelength, which is 1 meter.
Yeah, and then C is what is the speed of sound based on this experiment?
We know the frequency, we know the wavelength. Speed is equal to frequency times wavelength. And so 300 hertz times 1 meter, 300 meters per second. And then I assume the last one is what's the size of the water column in order to get the third harmonic?
Yeah, and what height of the water column will the second harmonic be?
Yeah, I don't know why I asked what's the length of the water column. I know I did, but it's in the master set as opposed to the length of the air column, but I did anyway. So, I guess the big question is how many wavelengths is the third harmonic? And this is when there's a response in unison, bringing tears of joy to my eyes. or just getting stared at. That's good, I'm trying to stop you from staring. When I go to the next harmonic, how many waves do I add? Yeah, and I'm gonna add a half every single time. No matter what the setup is, when I get to the next harmonic, I add half a wave. Since for this situation, we skip even harmonics, there is no second harmonic. There's first, third, fifth. And so I'm gonna add a half a wave to that. So if that's my bass right there, and then I add a half a wave,
Was it 5 or 4?
was what?
Was it 4 or 5
What?
waves?
That's a quarter of a wave, this would be 3/4 of a wave. I feel like we're not in the same here.
Before you told me that 4 waves, it was third harmonic, and then you told me it was 5.
The third. Okay, this is the one fixed, one free. That's 2 free ends there. Before that. That's the 2 fixed ends. Looks like we skipped over this part. Yeah, it's missing. So when you have one fixed, one free end, we have a node at the fixed end, we have an antinode at the free end. And once you establish how many waves are in the first one, it's a quarter of a wave. The third harmonic would be 3 of those, the fifth harmonic, 5 of those, and so on. So this is 3/4 of a wave. And that 3 is what indicates why it's the third harmonic. I don't say, I just gave a test, and there were a number of students who started out with that's being half a wave, and they had to do the fifth harmonic, so they said it was 5/2 of a wave, which immediately threw them off, and then they drew something that was neither of those. Anyway, third harmonic, 3/4 of a wave. Well, I know what the wavelength is, so that would be equal to 0.75 times 1. So my air column is 3/4 of a meter. My air column is going to go from here to somewhere around there, and that's 0.75 meters. But I asked what is the length of the height of the water column. I'm asking for this. I know the whole thing is 1.75 meters. Therefore, this has to be 1 meter. That has to add up to that. Did I answer the question?
Yes.
Okay. Any other questions? Number 11. A proton travels to the left through a constant magnetic field, which is pointing out of the page towards you. All right. We had to talk about magnetic fields, but let's do it. What do you know about magnets? I'm guessing you've played with magnets at some point in your life. What's that?
Opposites attract.
Okay. And in terms of magnets, what are the opposites?
Positive.
Typically not. I mean, there are forms of mathematics which talk about a positive and negative end. However, typically with magnets, we don't refer to it as positive and negative side. Where does Santa Claus live?
North, south.
Yeah, north and south. So a magnet's got a north end and a south end. Magnetic field lines external to the magnet will go out of north, it will go into south. These are these sort of invisible lines that permeate. Until you get tired of drawing. So, if I just put a proton right here, just sitting there, it's not gonna be influenced by the magnetic field at all. In order to be influenced by the magnetic field, that proton needs to move. And so, there's a relationship between, well, in essence, the force on the proton, the force on any charge, just make it generically Q, is the charge. The larger the charge, the greater the influence. V cross B. Naturally, all those letters make perfect sense. Well, actually, Q at this point, I hope you realize that's charge. V,
Speed.
V for,
Speed.
it's a vector, yes, velocity. And B, that's the new one. That's magnetic field. Now, I believe he came up with B because the person who came up with that convention had needed to assign letters to several different vectors. The first one was A, the next one was B, the next one was C. So B happened to be the magnetic field. Now, it's a cross product. We have dealt with cross products before, but you might not be familiar with it. But let's think about it this way. Sten gun. Anyone know what a Sten gun is? British Commandos.
What?
All right, Sten gun. All right, Sten gun. It's a machine gun. There's a part out here that you hold as you fire. Magnetic field, you won't typically have a single line. Magnetic field, you have multiple lines. So basically, we're going to do the Sten gun. Use your right hand. Again, right, not dominant, for some of you. Use the right hand. The three fingers right here will be in the direction of the magnetic field. The finger, think about the bullet that comes out at a certain velocity. This is the direction of the proton, of the proton's velocity. And the thumb, think about it as a trigger. What the trigger does is it, in essence, start the reaction. It forces, ultimately, through a reaction, it will force the bullet out the barrel, so that's the direction of the force. So velocity, force, magnetic field. If that proton is traveling this way, well, that's the direction of my bullet. My magnetic field is going down. My thumb points in the direction the proton is forced. So that proton is going to be forced that way, coming at you.
Why isn't the magnetic field going towards us?
The way that I've drawn it, my magnetic field lines are going this way.
Yeah.
The force on the proton or or electron or any charged particle going through a magnetic field, the force is always going to be perpendicular to the velocity and the magnetic field. So in a two-dimensional problem like this, it's either going to be forced that way or into the other room. So if I have a magnetic field going across like this, and I take a proton and shoot it downwards, which way will that proton be forced? Index finger in the direction of the bullet. So you have it being forced that way. You have it, these go in the direction of the magnetic field. Index finger in the direction of the positive charge. Thumb points in the direction of the force. Coming at you.
Can you do that again?
All right, so magnetic field, it's actually labeling. Magnetic field is that way. So I put these three fingers in the direction of the magnetic field. My bullet, my proton's going down. My thumb So your magnetic field lines, yeah, there you go. And so the thumb points in the direction of the force. If you have some sort of contortionist circus kind of thumb, recognize this is just a trick. There's formal mathematics that goes along with it. Just because you can bend your thumb so it points in some bizarre direction, and I'm gonna label it bizarre, not meaning to thumb shame you, but that does not change the direction of the proton flow just because your thumb points in some, you can bend your thumb all the way back or something. So that particular problem was a proton travels to the left through a constant magnetic field which is coming out of the page. So in that particular problem, magnetic field's going out at you. Using that classic 3-dimension, if you got the dot, it's coming at you. If you get the cross, it's going away from you. So magnetic field's going this way. Proton is moving to the left, which I think is that way. Proton is moving this way. So magnetic field coming out, proton going to the left. It's going to be forced upwards. As a matter of fact, if I've got just a really big area here with a magnetic field, and I shoot a proton into it, I'm going to start down below. Shoot a proton into it, it's going to be forced upwards. But once it starts being forced upwards, it's still going to be forced perpendicular to the motion, and so it's actually going to travel in a circle in a centripetal motion form. Now suppose I took an electron and shot an electron into it. Which way will the electron be forced? The equation still holds except for the fact that there's now a negative sign popping into it. Nope, that is not a vector there. Q is now negative if it's a negative charge, which means that the direction will be the opposite as if it were positive. So if I shot an electron into it, I can do it two ways. So I can go, well, I got an electron going this way, my magnetic field's going out, my thumb points up, the electrons are the opposite, so the electron will be forced downwards. Or I have an electron going that way, that's the same as a proton going this way in terms of forces.